So isomers. So why are we talking about isomers?
Isomers. To be honest, it was a section in the textbook that I thought we hadn't covered yet. But
Okay.
to further kind of explain, I think isomers are a little topic that gets mentioned in 1 or 2 slides in a PowerPoint presentation in a lecture. But I think isomers are just so interesting because there's just a lot of good chemistry, even if it's not even discussed too much in this course.
Yeah.
There's just a lot of good chemistry that maybe some students will find this interesting or at least helpful.
So isomers. Yeah, I think in this course, isomers merit about 1 or 2 slides and not too much more. If you're thinking about being a chemistry major, it matters. If you're probably if you're thinking about majoring in biochemistry, and there are some very interesting biological effects associated with isomers. But before we get into that, if we get into that, let's just kind of do a rundown of what an isomer is. So an isomer, you can't ever just have one isomer because something has to be an isomer of something else. And so you always have more than one if you're going to have them. And basically they are, it's 2 molecules with a single molecular formula. And so they have the same chemical formula, they have the same molecular formula, but they're put together in 2 different ways. And we're not going to worry about them too much in this course, but there are things that are kind of like isomers that we're going to worry about quite a bit. But let me first start off by showing you what I will call regular isomers or which are structural isomers. And this only makes sense if we worry about this in this course where we have started to understand how many bonds various compounds can have. So I'm going to give you a single molecular formula, C3H7OH. Okay, propanol. It's got 3 carbons, that's why I call it propane, propanol. Propanol, okay? And I'm going to put this together by joining 3 carbons together. And I know that carbon likes to have 4 bonds, so I'm going to put 4 bonds around each one of my carbons. And if we count those up, 1, 2, 3, 4, 5, 6, 7, 8, I've got 8 atoms that I can bond to it. I've got 7 hydrogens, and I've got an oxygen and a hydrogen left over. And the way I'm going to do this is I'm going to put a hydrogen on each one of these bonds, and then I'm going to put this OH, this hydroxy, this on the 8th one. And so I have some choices. I can go hydrogen, 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 OH, and I can end up with my OH on this central carbon, or I could do it starting somewhere else, hydrogen, 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 and I can end up with my OH on this end one over here. And so I'm going to draw both of those. And so I'm going to go 1, 2, 3 for my carbons, 1, 2, 3 for my carbons, 1, 2, 3, 4, 5, 6, 7, 8 bonds, 1, 2, 3, 4, 5, 6, 7, 8. How am I doing so far?
Looking good.
Great. And so all I'm going to do that's different on these ones is I'm going to put an OH here on this second middle carbon, or I'm going to put my OH over here on my end carbon. So I've got 1, 2, 3 carbons, 1, 2, 3 carbons. I've got my OH and my OH, and now I'm just going to put in my 7 hydrogens. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have two compounds. Each of them has 3 carbons. Every carbon has 4 bonds, just the way we would like carbon to have 4 bonds. They've each got 1, 2, 3, 4, 5, 6, 7 hydrogens. 1, 2, 3, 4, 5, 6, 7 hydrogens. And then they've got this OH. So they've got the exact same formula, exact same molecular formula, exact same chemical formula. But the way they're put together, their structure is a little different. In this case, I've got the OH down here on this end carbon. In this case, I've got the OH on this middle carbon. And so those are called structural isomers. And we would call this one, we might call it propanol. Maybe if we wanted to really belabor the point, we might call this one 1-propanol, because my OH is on the first carbon. Or, and in this case, if this were a 1-propanol, this one we might call 2-propanol, if we were going to write it shorthand. And there's another way that we might write it as well, which is to say, we would put this 2, which says, hey, this 2 is telling us where this OH group, this alcohol OH group is. And so I might call it prop and 2-ol. And I might call this one prop and 1-ol. You might see those sometimes when you're doing them. But that's beyond the scope of this course. That's something that you might worry about in your next chemistry course, or if you continue on to organic chemistry. The important thing for us is to show you, hey, it is possible to make very legitimate chemical formulas for 2 different compounds that have the exact same chemical formula. And in this case, they're different based on the way they are structurally put together. And so we call these structural isomers. What do you think of that, Kevin?
Yep, great breakdown of isomers.
Is there something else that you want me to talk about with this? Because I've got one other thing that comes up a lot more in this course that's kind of related to isomers that I can bring up too.
I think you gave a pretty good example. There can be a lot more isomers than just 2. Sometimes some compounds can have 3, 4, 10 isomers with more atoms. It's just maybe drawing it out and practicing it if there are any problems with isomers.
Right. And how about I could, if I could demonstrate how easy it would be to do that. If I had 1, 2, 3, 4, 5, 6, 7, 8 carbons. We've probably talked about octane in this course. So here are 8 carbons, oct, and that's why it's called octane. And I could surround that with hydrogens. But you can imagine that if I made octanol and I put a hydroxide on there, I could put a hydroxide on this carbon, on this carbon, on this carbon, on this carbon, and that would be 4 different compounds with the exact same structural formula. So 1, 2, 3, 4, 5, 6, 7, 8, and I'll put OH, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to put my OH here this time. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to go right here. How am I doing? So I haven't finished the rest of these compounds. I haven't shown all the rest of the hydrogens, but you can already see that having this OH group in all of these 4 different positions could give us 4 structural isomers for octanol. Mm-hmm. And that's before we even start moving some of these other carbons to other positions, which we can do as well. So you're right. The first example I gave of propanol, there are really only 2 structural isomers for this compound, but it gets a little longer compound, and you can have a lot more isomers. All right, so this is a place, they're not isomers, but you have to think about them in a very similar way. So when we're doing Lewis structures, and we're trying to figure out what are the most stable structures at various times, we're going to be rearranging electrons and bonds frequently to try to figure out what's stable. And we do something called resonance structures. And a very convenient one is carbonate, CO3 2-. And so it's related into isomers in the sense you got to think about different ways in which this can be put together. So here is a carbonate, 1 carbon, 3 oxygens. And when we build that Lewis structure, we're going to discover that to get the carbon with 4 bonds, we have a double bond and 2 single bonds. To get the oxygen, having the right number of electrons, we're going to put 1, 2, 3, 4, 5, 6, 7, 8 around that oxygen. And we're going to put 1, 2, 3, 4, 5, 6, 7, 8 around this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. And that uses up all of the electrons that we have in the carbonate. And 1 negative charge is associated with this oxygen, and 1 negative charge is associated with this oxygen, which is how we end up with carbonate being 2-. It's a very straight, reasonably stable structure. However, there's nothing that's really different about these 3 oxygens. And so another way of drawing that is to draw my carbon like this and have my double bond over to this oxygen and have single bonds to this oxygen and this oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. And so then I would have a negative charge here and a negative charge here. And so these are, we wouldn't call these isomers, but they are different ways of drawing or writing the structure of carbonate. And if you can rationalize that, if I can move my double bond from here to this position, then I could do the same thing and move it from here down to here. And so for carbonate, we would draw 3 resonance structures. 1, 2, 3, 4, 5, 6, negative charge, negative charge. And so that's 3 different ways of writing the structure, the structure of carbonate that are all equivalent. And kind of like isomers, it's a way of thinking about different ways in which you can write them. But in this case, the resonance structures say, hey, this is a way of saying that this compound, this molecular formula is very, very stable. If we can write 3 different ways of saying it's 3 different ways of writing it equivalently, we would say it's more stable. And so they're not called isomers, but they're a way of thinking about different ways of putting molecules together, or putting, in this case, putting an ion, a carbonate ion together. And so that's another way of thinking about different ways of putting atoms together. So I don't know if that clouds the issue at this point, but it's more pertinent in terms of rearranging structures for this course than isomers are.
Yeah, I think I never really thought about it that way. I've never been taught it like this, but the idea of rearranging atoms to make different molecules and get different results is maybe a better way for you to remember both of these concepts better.
Yeah,
so.
Maybe. Yeah. It'll be different anyway.
Yep.
Yeah.
This is all then.
Okay. Awesome. All right. Thank you. Then I'll talk to you again next time.
Yep. Talk to you again, Dr. Hunter.
Is that what